My purpose in this video is to give you a little more detail on Kepler's laws, a little bit more than we had in the historical overview that you may have just watched. And the first law is just the law of elliptical orbits, that planets move in elliptical orbits. And the sun is at one focus. All right, so here's a picture of that, a graphic. Here's our planet in orbit, and we have the two foci, F1 and F2. F1, we're going to call the location of the sun. So that's where the sun resides. Now, I wonder what resides at F2. Can you figure it out? Can you guess? Some people might say Earth or another planet, but that's not true. The planets are on this elliptical path. This is the other focus. Is there another star there? Well, there doesn't actually have to be anything there. In fact, there better not be. If there is, it'll probably just slam into the sun gravitationally. So basically empty space here. All right, so there could be stuff, particles, fields, space itself, but essentially empty. Okay. Then we have some other important features here. We have the location on this path that's closest to the sun. In fact, when the planet's here, it's perilously close to the sun. The perihelion. The aphelion is the furthest distance away from the sun. The planet is apt to fly away from way over here. Now you remember how to remember these two locations. We have the semi-major axis. The major axis is through the longest dimension through the ellipse. Half of that from the center to the edge is the semi-major axis. And the average distance from the planet to the sun is this semi-major axis. And what that is, it's the average of the perihelion and aphelion distances. So perihelion plus aphelion, that's the entire ways across here. The average of that is, just add those divided by 2, we get the semi-major axis. So that's the average radius. So we have A and we have B, and the average radius is also A plus B divided by 2. All right. So if we think of the planet being over here, and we have this blue line being from here to here, the red line being from here to here, and that really together, A plus B, is the distance across here. That divided by 2 is the semi-major axis. So it is A plus B over 2. Now, eccentricities of the planets. Eccentricity means how, off kilter. An eccentric person is someone who is what? A little off. So the eccentricities refer to how off from being circular they are. Now, the planets in our solar system in particular are almost on perfect circles. They're not perfect though, but they're quite circular, but yet their centers, the orbits, are offset from the sun. I'm sorry, really what we should say is they orbit the sun. The centers of the circles, or the paths themselves, are not located with the sun. So here's Earth, for instance, Earth's path around the sun, Mars' path around the sun, okay? And you'll notice that if we take the center of Mars here, you notice that it's not coincident with where the sun is. So that makes the orbital path less circular than it would be from just saying, like, looking at this idealized ellipse here. The very center, this ellipse looks more circular than orbiting around from the sun. If we orbit the sun, which we do, then it's extremely non-circular, if you know what I mean. Okay, so X is the center of the Mars ellipse. The sun is what Mars orbits, so they're more off-center. Okay. And now a little bit more, just defining here what the eccentricity is. The eccentricity is C over A, And C is the distance from the center to a focus, and A is the semi-major axis. If you take the ratio of those two, that gives how much eccentricity you have. The biggest it can be is if these foci move all the way over to the edges where the distance from center to the focus approaches the semi-major axis and the eccentricity approaches 1. These two values are the same. And the smallest it can be is a perfect circle where the focus comes all the way over to the center, meaning that the distance from center to focus is 0, and 0 over A is 0. So that defines the range for the eccentricities of the orbits of the planets. And now Kepler's second law, the law of equal areas. This is pretty amazing because Kepler really didn't know the fundamental reason for the laws that he actually came up with. He was just a very good mathematician, very good at sorting out the data, and he made some observations and pieced it all together. Well, one of these is the second law, as we call it now, which is the idea, the reality, that if you join a line from the sun and the planet, that line will sweep out equal areas in equal amounts of time, equal time intervals. So that's a pretty surprising thing without understanding why. So here we have the sun, we have the planets, and I show 1, 2, 3, 4. So over here, it's moving at V1, okay, V1, and it goes from 1 to 2 in delta t. Then later on, well, first of all, let's show that in that interval, we connect lines from the sun to the planets in 2 places, and fill in that pie slice, it's area A1. Later on then, from positions 3 to 4, the same delta t, if we connect those lines and look at the area, namely call it A2, you'll notice that the planet's moving faster here. But what about the area here versus here? The amazing thing is that Kepler discovered the areas were the same. And that's true no matter in what part segment of the orbit we're talking about. Let's consider a circular orbit. Here we have positions 1 and 2, radius r, the distance in delta t. Now the distance in delta t, to make this simpler, actually to make it more accurate really, is that what we're really talking about is a really small interval. In a small interval of time, then the triangle is really skinny, right? Much skinnier than this, much more than this. This arc length and a line connecting 1 and 2, those two distances end up being the same as delta t becomes very small. All right, so that's calculus thinking. But those two lengths, the arc length and the actual chord length, become the same as delta t approaches 0. Which means that we have a skinny triangle, and the area then is 1/2 the radius times the d. Okay, so that becomes the exact area as delta t goes to 0. With that as background, we can now look at our real planetary system here, which is highly elliptical in this case, and recognize that these triangles are really like you approach t is equal to 0 and you have little tiny right triangles essentially. Then A1 is equal to 1/2 R1D1, and A2 is equal to 1/2 R2D2, R2D2, C3PO, R2D2. Okay, well, get off of Star Wars here for a minute. The time delta t is the same for both, by definition. R2D2, oops, sorry. V delta t, that's what distance is, velocity times time. And area 1 is equal to area 2, so let's set these equal. And let's replace the d's with the v delta t's. So we have A1 is 1/2 R1V1 delta t, A2 is 1/2 R2 V2 delta t. And so when we set those equal, the 1/2s and the delta t's go away. And so we have a relationship. R1 V1 is R2 V2. is r3v3. In fact, at any instant, the radius times the velocity is a constant. Now that's almost the truth. I've been telling you a white lie. Shame on me. I will now come clean. Yes, I will come clean. So here we have the sun, planets at radius r here, 3r over here. So first of all, based on what we just learned, if the planet's moving at velocity v, you see the vector drawn there, and over here, 90 degrees, as it was with the radius here, it is over here as well. If this is 3r, you can use this idea to recognize that this speed is a third, or the velocity magnitude is a third of what it was at the perihelion. Here we're at aphelion. But what about this situation? What about when the planet's at some intermediate point? Now the radius and the velocity are not perpendicular. Can we just multiply those two together? Well, the answer is no. Doesn't work that way. We actually have to consider the perpendicular component of the velocity to the radius. So this is how fast it's moving perpendicular to r. And so the real truth, if you can handle it, is that at any instant, v1 perpendicular r1 is v perpendicular at velocity 2, r2, any position. So the perpendicular velocity to the radius is true anywhere. It's actually a consequence of the conservation of angular momentum, which most of you viewing this have not learned about yet, but nevertheless, that is the story for our planetary orbits. Law number 2. And now let's go on to law number 3. Well, last but not least, we have Kepler's third law, which relates the orbital period of a planet going around the sun and its radius of orbit. And this again is pretty awesome how Kepler discovered this mathematical relation. Again, as I repeat, he did not understand why. He was just making observations. So he was very kinematics oriented. In other words, describing the motion. And he discovered over and over that the ratio of the radius cubed over the period squared of the orbit is a constant. It's a constant. It's a constant for our sun. It has a particular value for anything orbiting our sun. So here we have planet 1 and planet 2, two different radii, two different periods. And so if you take that ratio, it's the same for all the planets. Now for Earth satellites, that would include the moon also, because the moon is a satellite of Earth. And other satellites we place in orbit around Earth. R cubed over t squared is k Earth. It's also a constant, but a different one than the constant for planets orbiting the sun. So this is very useful for us. With this, we can solve some really useful problems. So let me model for you how to use this relationship to solve planetary problems or orbital problems, like this one. So we'll use Kepler's third law. The period of the moon is 27.4 days. Let's determine the period of an artificial satellite orbiting very near the Earth's surface. So basically what we're going to get out of this is the period of orbit right at the surface of the Earth. Now the radius of Earth is given here. The moon's orbital radius is given here. So we have the Earth, and right around the Earth is an orbit, and then way out here is the orbit of the moon around the Earth. So it follows this correct pattern. They're both orbiting Earth, so r cubed over t squared of the moon is r cubed over t squared of the satellite. Both have the same value, and we're not particularly looking for that value. It doesn't even matter what this value is at the moment, but that it's a constant enables us to relate these two and solve for what we're looking for. We're looking for this quantity here, the period of the satellite. Well, we can use a little manipulation, do a little manipulation, and get the periods together and the radii. So the periods, the ratio of the periods squared is the ratio of the radii cubed. And now I set it up this way because we want to isolate period of the satellite. So the period satellite is t moon squared over the ratio of the cube of the radii, satellite to moon. And now let's square root both sides, and we get this. So there's the form I really wanted in. We're ready to put our numbers in. So the period of the satellite is the moon's period. Now let's choose whatever convenient unit we want. Well, we were given it to us in days. Let's keep it days. We'll put 27.4 here. That means the end result should be in days as well, as long as this is dimensionless. But it will be dimensionless, because no matter what we put for units for the radii, it'll be the same here, and they divide out. So a big point I'm making here is don't convert units. You do not have to convert radius to meters. You don't have to convert period to seconds. Just leave it in the form it's given, and it will all work out. So here we go. 27.4 D for days, and here is the radii. Now they were given in meters, so that's great, and it doesn't matter, again, they'll divide out. So the third power and then the square root, that's the 3/2 power. And so period of the satellite is 0.058 days, which is 1.4 hours. And if you recall, earlier in this unit, we computed the period of a satellite around Earth and got the same value. So that will conclude our somewhat extended introduction of Kepler's laws. See you next time.